Hello and welcome to this video. In this video we're going to be looking at satellites. So this will be the last section of gravitational fields, which is just looking at the applications, the real life applications. How does this stuff actually work? What would we put in a gravitational field other than stars and planets and things like that? So we make use of these laws of physics by sending satellites into our atmosphere or above our atmosphere. And in the spec, what you guys need to know is 3 different types of satellite orbits. So the first type, and probably the one that's going to come up the most, is called a geostationary orbit. Now, this is kind of a self-explanatory name. Once you've heard it the first time, it kind of makes sense the second time. Geostationary orbits orbit the Earth where the time period of the orbit is the same as Earth's. Okay, which means that it is constantly at the same point above the Earth at all times. Okay, so it remains above a single point on Earth at all times. Okay, now the thing with this is that the Earth has an incline. When Earth rotates upon its own axis is not necessarily what we would consider to be vertical. It's actually like 32.5 degrees to one side, which means that if we were to just go completely horizontally around the Earth, we would end up moving positions even if the time period is the same. So if I have, for example, let's say this is the Earth, okay, this is the North Pole and this is the South Pole, okay, and this is the equator, right? If I had an orbit, which I'm going to put in a red pen, if my orbit was just like this and I orbited around this circle and then I went around the back there, notice how my position on the Earth actually does change as I move around. Okay, this is not a geostationary orbit. Okay, a geostationary orbit lies on the same plane as the equator, so it will orbit around this line and it will stay like this. Okay, so they must orbit around the same plane as the equator, and this is the only thing that separates them around the same plane as equator. So this is the only thing that separates them from the geosynchronous orbit, okay, which we'll look at second. The uses of this are pretty standard for most things, for most satellites. Like our uses would be things like communication. So your phone works by sending signals into outer space with these satellites or into our atmosphere, depending on how far away they are. The satellite then receives the signal, bounces it back to a different position on the Earth. And so communication is one use for all 3 of these types of satellites. We can also look at the weather. So we can do weather monitoring and also surveillance. Just by setting these satellites up to observe the surface of the Earth. Now this surveillance one for geostationary orbits is going to continue on to GPS. Okay, this is while the rest of them can do surveillance, their kind of surveillance would be just a brief overlook, just to observe, I don't know, heat transfers or how polluted a certain area is, and it will map different parts of the Earth. If we've got something sitting above a single position on the Earth, where it is always going to be above that position, it can monitor this position for any signals that come directly out of this. So if we have this GPS, and if we imagine we looking at a map, let's say that above the surface of the Earth at some distance away that you can calculate, there is a satellite at this point here. Okay, and on the surface of the Earth there is a phone that sends a text message and a signal pings out to all the satellites, and this satellite can view a cone which fills this region of space. Okay, so if this satellite detects it, it means that the phone must be within this radius of the satellite. Okay, but this isn't the only satellite in space. We have loads of satellites in space. So if we had another one that was, for example, here, that could also detect a ping in this radius. Okay, so if both of these satellites detect it, we know it's somewhere in this middle gap here. Now if we had a third one down here, and then we say that actually this one can also detect that, then we've pinpointed it to this location here. This is the location of the phone. This is where the phone is. Okay, so if you've got a GPS in on your phone or on any kind of device, the way it works is by constantly sending out signals to satellites. Satellites get the signal. A few satellites will each be in a network that will work together to triangulate the position. So this is the process of triangulation. And they then send you back your position on the map that they're viewing from above. And this kind of then follows a similar process to seismology, where you detect the epicenter of an earthquake from things like this, but the process of triangulation is the same. Okay. So the difference between this and then geosynchronous orbits, so the second type of orbit we're going to look at is geosynchronous, is that the synchronous part of the geosynchronous orbits means that it still has the same time period as Earth. So it still has the same time period as Earth. However, geosynchronous orbits don't stay in the same position above the Earth at all times. They will be inclined to the equator by some amount, and that will then change their position above the surface of the Earth. So they will be inclined around the equator, and then leads to different positions. So it will move around different positions. And to compare that to the previous example, if this is Earth, and this is the North Pole, and this is the South Pole, and this is the equator, that means that a geosynchronous orbit will do something like this, and it will orbit around here, or it will orbit around here like this, or something like this. It will never be along the same plane as the equator like a geostationary orbit is. And that is because they will then monitor different sections of Earth. Their uses will be very similar. They can still be used for communication, although it would be very different types of communication. This type of communication would be communicating between different sides of the Earth. The communication with a geostationary satellite would be sort of like a local area network. You can still have weather management, you can still, or observations, you could still see how cloud patterns are going to move. If you're moving across the Earth, you can then see where the clouds are going to go, what kind of temperatures are happening all around the world, and then you can look at things like air currents and see what direction everything's moving in, and you can still do surveillance. But again, this will be a different type of surveillance. It's not going to be a GPS type of surveillance. This is going to be more of just a general watching over the Earth kind of guardian surveillance, I guess. Now, the thing that I want to get through with the geosynchronous and the geostationary orbit is that because their time period is the same, we have to then assume that using Kepler's law, they have the same orbital radius. Now, there is often questions that are asking you to calculate the height of the geosynchronous or geostationary orbits, and you want to use Kepler's third law for that. You want to say that t squared is equal to 4 pi squared over gm r cubed. So we know then we could rearrange this to be that r cubed is gm over 4 pi squared times t squared. And then we know t because it's going to be 24 hours, because that's the time period of Earth. So this is 24 hours. However, you always want to make sure your times are in seconds. M is given in the formula sheet, G is given in the formula sheet, so all you have to do then is solve for R. Be careful when they ask for the difference between the radius of orbit. The radius of an orbit is not the same as the height above the Earth, okay? The radius of orbit starts at the center of the Earth. Okay, the height above the Earth starts at the surface of the Earth, which means if we were to then start, if we were to look for the height above the Earth, this is the radius of the orbit minus the radius of Earth. So this is the radius of orbit minus the radius of Earth, which I'll just write here. So RE being the radius of Earth. Okay, and so I'll leave it as an exercise. You can go to the formula sheet and get the mass of the Earth and the gravitational constant, and then you can calculate the distance from the Earth and then the height above the surface. And then you can Google it and then see if your answers make sense. The last kind of orbit we have are polar orbits. So polar orbits differ from the other two because then they have nothing to do with the time period of Earth. They can actually orbit Earth much quicker than the time period of the Earth because they're much closer to the surface. So they're kind of low orbit satellites that will pass over the poles of Earth. So they pass over the poles of Earth. And now what I mean by the poles of Earth is the North Pole and South Pole. So if this is Earth and this is the North Pole and this is the South Pole and this is the equator, a polar orbit will look something more like this, and it will orbit around North and South Pole, going across there in a lower orbit, which means faster than Earth can rotate. Okay. Now this is also going to be used for same sort of things. I will say polar orbits don't come up in questions as much, but it is good for you to know that there are more types of orbit and just get a general idea of what a polar orbit is. So it can still be used for communication. It would be more the similar type of communication that geosynchronous orbits have, where they can communicate with other sides of the Earth, especially in this case because it's traveling faster than the orbit of Earth around its own axis. It will then be able to go and send signals to other positions much quicker. And we can also use it for weather monitoring, seeing how wind currents are going to change going there. It's actually probably more reliable from this perspective because you're much closer to the surface of the Earth. So actually from here you can probably see more of the cloud patterns moving across and being able to measure wind currents and something like that more accurately. And we can also have surveillance of Earth, whether that's monitoring weather patterns or whether it's creating mapped satellite image of Earth. So if you go on like things like Google Maps, you can get a satellite image from what a satellite would see, and those are taken from things like this. So that would be that kind of surveillance that these would do, because they're much closer to the surface of Earth, so they'd be able to get a much clearer picture than something that's in a geostationary or geosynchronous orbit that's maybe another 100 kilometers back, so wouldn't have a good enough resolution to actually depict it. So this is everything you need to know about satellites. In terms of the questions that come up, they will usually use satellites as examples for things orbiting, so you can actually do calculations with potentials or field strengths or forces or orbital velocities or any of the kind of expressions that we've looked at so far. They don't really ask you too much about the content. I think the most important thing you want to take from this video is that geostationary and geosynchronous orbits have the same time period as the Earth, which means their time period is 24 hours. But always remember to convert it into seconds. Thank you for watching.